Welcome. This is the 7th lesson in the unit on exponential functions. This is our final lesson, so watch this tonight. Come in with questions tomorrow. We will do the practice together. And then what you will be doing is just reviewing for the quiz the next day. So, or the day after. We'll see what that looks like. So we'll see how many questions you have. So solve the exponential equation. This is just showing you different ways that we can solve this. This principle right here is so important. If you have b to the x equals b to the y, our bases are the same. That tells us that x and y must be equal. Okay? So if we have 2 to the x minus 1 equals 32, our whole goal is to take this 32 and write it with a base of 2. 32 can be broken down to 16 times 2. So there's 1 2. 8 times 2, there's another. 4 times 2, another. And 2 times 2. So you have 1, 2, 3, 4, 5 2's in 32. So you would say it is 2 to the 5th. Now, because our bases are the same, we can just set our exponents equal. That is the property of equality for exponential equations. And it really should make sense. Come see me if it doesn't. Now we just solve for x, add 1 to each side. We get x equals 6. Okay? Now we have 9 to the 2x. We have 27 to the x plus 1. What could each of these be written as? They could be written as 3. 9 can go to 3 squared. 27 is 3 cubed. Now we can wipe out our bases again. Oh, that's not what they did next, sorry. So now they go 3x plus 1. And now we wipe, no we don't. They're going to have us carry that throughout it. So they take 2 times 2x, is 4x. 3 times x is 3x plus 3 because you distribute it. Now they have us wipe out the bases. I was definitely getting the horse in front of the cart. Sorry about that. So now 4x equals 3x plus 3. We subtract 3x from each side. We get that 1x equals 3. Now you should be able to go back and plug that in. 9 to the 2 times 3 should be equal to 27 to the 3 plus 1, or 27 to the 4th. And you can actually do that on your phone, on your calculator, and raise it to a power. 9 to the 6th, 27 to the 4th, they should be equal. Okay, reflection. Show how you can check the solutions of the equations are correct. Well, you could plug the solution back in just like I just did and verify that it's correct. That's probably the easiest way to verify it. Okay, in the property of equality for exponential equations, explain why b cannot be equal to 1. B to the x equals b to the y. Let's review this. So it makes sense if we have 2 to the x equals 2 to the y, because 2 to the x has only one value that it can possibly be. Let's say that's 2 to the 4th. That can only be 16. Okay? But in 1 to the 4th, the value is 1. 1 to the 5th, the value is 1. And we aren't going to say that 4 is equal to 5. Because then we'd have to apply it to this, and 2 to the 4th is not going to be 2 to the 5th. Okay? 1 is a special critter a lot of times. So that's why this property says for any positive number be that other than 1. Okay? How would you solve the equation in part A if 32 were replaced by 0.5? Let's go up and do that. Okay, so 0.5. So we have 2 to the x minus 1 equals 0.5. What's 0.5 equal to in fractions? 1/2, I hope you said. So now we need to bring 1/2 to a base of 2. That means we're bringing it back up on top. So it would be 2 to the negative first because we brought it to the top. Now we would say x minus 1 equals negative 1. Add 1 to each side. And we have x equals 0. Okay? If you plug that in, 2 to the 0 minus 1 is 2 to the negative 1. 2 to the negative 1 is equal to 1/2. Okay? Whew. Those are fun. Love them. Now let's go to this, this application that we have here. We have a situation here where we want to look at the population of the United States in millions from 1790 to 1890. So first thing is up here on the graph, population, and it does say in decades. X is the number of decades, so population each decade from 1790 to 1890, and then I just put US. So US population, okay? So it tells us that the Y is the population in millions. So remember, I've told you a lot of times, these axes are so important to make sure and mark. Population in millions. It says that the x-axis is the number of decades since 1790, so decades after 1790, and then just follow along the number pattern. So 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 10, 20, 30, 40, 50, 60, 70, 80. Okay? Now, the question is, in what year did the population reach 45 million? Well, there's a couple different ways that we can solve this. I want you to describe a method you're choosing to do. Okay? I can think of two systems. If we write this, we want to know when 4.1 times 1.33 to the x, that comes from the equation right up here. We wrote it in our solution. We want to know when it's equal to 45 million. So you've got some options. You could go algebraically. First thing we'd do is divide by 4.1. Go ahead and do that. And then you'd get 1.33 to the x equals some number out here. And then you would have to start estimating, unless you know how to solve that algebraically. If you do, I want to see it. That's a cool thing to know. And you can Google that. Please, please, please Google it. See if you can figure out how that works. Okay, if you can't get to a result that way, you could always split these into separate functions. F of x equals 4.1 times 1.33 to the x. Make a table of values. You know, you're just going to go on x from 1 to 10, because that's what we've limited ourselves to. The f of x, you would need to plug it in using your calculator and get your values. Okay? And then you'd need to find out about when it hits 45 in the f of x. And then start breaking down closer and closer to get as close to 45 million as you can. Another option would to do this as a system. This is the first graph that you'd graph up here. And the other graph, g of x, would be the other part of the equation, 45, which will just be a straight line right at the 45. So you choose which way you want to do it. I want to talk about that tomorrow, see what you guys end up getting. Solve this using an exponential function, linear function, to form a system. Show both on the graph above, interpret what their intersection indicates. So here I want you to interpret, once you've graphed this up here, once you've graphed the curve and graphed the straight line, what that point of intersection indicates in the context of the problem. So you'll have to explain in population and decades what it means. Okay? Next page. Camellia invested $300 at 4% interest, compounded continuously. Okay, so you know that we're going to be using E, right? Diego invested $275 at 6%, compounded continuously. When will they have the same amount of money in their accounts? So let's go to Camellia. $300 is the principal. The interest, change it back to a decimal, so 0.04. And Diego is 275, e raised to the 0.06. So we're trying to figure out when those will be about equal. I want to see, really, I want to see how you come up with that. Be inventive. Even Google that, see what they show you. I want to see how many different solutions we have, and I want you to try to make sense of those solutions. So please look that up, and then answer these questions. Who has more money in her account? Choose Camellia or Diego. And how can you observe the difference in the accounts after 10 years from the graphs and the equations? I will not be going over this unless people come to class having watched this and they're prepared to discuss what they could Google and find. And this is an important one for a future test. I want to know exactly how you see to do that. Okay? It does explain in here how to graph it on a graphing calculator. I can show you that, but I would really, really like you to investigate on your own. There are graphing formats on the internet where you can actually plug this in and graph it and make sure that it makes sense, but I just want to see how many different ways people choose to solve it. Okay? Tomorrow in class, we will talk about the practice. That was it for tonight. Have a good night. That's lesson 7 of the unit on exponential equations.